In other ways, yes. But
okay, so your assignment this week is, last week you developed a student class, and importantly last week when you were storing values like the names, you were storing those as strings in character arrays that were allocated off of a stack, right? They were statically sized arrays when you declared them. Looking for some hint of acknowledgement.
yes,
That's what
yes,
we did, right?
yeah.
So the benefit to you was that made it easy to write the code.
Easier.
Okay, easier than what you're going to do this week. Okay, so remember that if you declare some string like this, the benefit is easy. What are the cons? And I have a couple of cons that I can think of. But
Scalability.
okay, well, I guess that's both of mine. No, that's one of them. Okay, that's one. Scale.
Yeah, that was right.
So, scalability. What do you mean by scalability?
Well, to add more members, you're gonna have to write the exact same amount of code. Like, yeah, like
over and over
yeah,
and over again.
for each one, yeah.
Yeah, we had to do it over and over for each one. Okay. What does this do to you?
Well,
Make it sad.
So let's say that you have somebody with a long name, a really long name, a really, really long name. Okay, you might not have enough room, right?
Yeah.
So you probably made this a large number so that you wouldn't run into a problem, right?
So then you have a lot extra.
So you either are too short for some cases, or too long for some cases, right?
yeah.
Now, if it's too long, that means you're using more memory than you need to with your program. If it's too short, you're either truncating the user's information in order to store the part that you can store, or you wrote sloppy code and you're writing past the end of your array. One of those two things is happening, right? Writing past the end of the array has the capability of crashing your program or causing other unintended results. Truncating the user's information is the desirable outcome of the two. But you end up in one of those two cases there if we don't have enough space to store what we need to store. You have no flexibility. The 128 is compiled in. It's there at build time, and you can't change that at runtime. Okay, so those are the things that we don't like about this. So we're going to fix it today. We're going to fix it by moving to a heap model where we're dynamically allocating memory off the heap as we need it. So with this model, we declare our variables as character pointers. When we find out how much data we need to store, we allocate it from the heap. And we allocate exactly the number of bytes that we need, thereby overcoming these two issues. It won't be too short and it won't be too long. It'll be just right. Goldilocks will love us, right? So, but then the problem comes in that if we forget to deal with this appropriately, we'll leak the memory at the end. Leaked memory is memory that was allocated off of the heap that we no longer need, but we don't allocate to the heap. We don't give back to the heap. So somewhere in our code, we'll we'll need to have a delete statement in order to free that memory back up. So these are the basic changes that are going to be necessary for this assignment over the last assignment. Now, along with that, since we're dealing with classes, we come into a few new methods that we need to develop for our classes. Can I erase this again? All of my wisdom going away. So let's say that I have a student object. And I do a bunch of work down here to populate the student object. And so forth, right? Now, if this is our newfangled student object that actually supports dynamic memory, then it's going to allocate 7 characters to store this, right? 6 for the letters and 1 for the terminating null character at the end. Then, let's say later, I have an additional student object I create, and I want to make it have all the same information as the student. I want to duplicate that object through assignment. Well, that's legal syntax, and with our previous iteration of the student class, there was no problem with that. The compiler would set things up appropriately so that for every data member in the student class, that data member is copied across to S2. We're going to go to the right here. Maybe we'll come over here. Okay, so let's think about my STU object here that has within it an M last name data member. The model that's on the far board over there is itself a pointer to some location in memory that stores my last name in, right? I won't fill in the rest of the details if that's okay. Well, that assignment operator that we have over there is perfectly happy to take S2 and for every data member of the student class, copy the value from STU into S2, which means that S2 gets a copy of that same pointer, so it's pointing to the same memory location. It's not a duplication of the data, it's just a duplication of the pointer. And that would happen if either of these were assigned into a third student object, right? So all student objects that were copied from this original source would be pointing at the same piece of memory here. Okay, which causes a problem then if I go down here and I copied that, but I actually ended up wanting to change the last name. Ooh. If I change the last name, what happens?
That changes it for both STU and S2.
Okay, so in the simplest form where you're trying to copy over this, it would copy over that, right? And they both haven't changed. In our new modified version of set last name, it's actually going to even be worse than that, if you can imagine. Because Simpson doesn't fit in the same space as Larson, right? So what's going to be necessary for the set last name to allocate some space off of the heap, big enough to store the string Simpson, And then the student class, the set last name method, will assume that this memory is no longer needed. As such, it will call the delete call on that memory. And then it will make this pointer point here. Remember, the delete call has been called on this. Our program proceeds along. At some point, the stu object tries to fetch last name. When it does, this pointer is returned, and the code tries, receives that return value, tries to access the data stored here. The problem is it's been free, so there's no guarantee whether the contents will be what they're supposed to be or not.
Sounds like it difficult.
Okay,
Something not want.
so it's not something good, right?
Right.
So in order for that to work correctly, we're actually going to create a method called operator equal within our student class that overrides the functionality of the assignment operator when it works on two student objects. And it will be intelligent. It will know that last name is a pointer to dynamic memory. So rather than copying the pointer, which is what we had done before, at the point the assignment occurs, S2 will allocate its own dynamic memory, copy the contents from that dynamic memory, and point to its own piece of memory.
But then there's still going to be that other one that says Simpson, right?
Sorry, I'm rewinding the clock
Oh, okay.
back up to here.
Okay.
So when we have this operator defined, it will be set up such that now when we say set last name Simpson, then this gets deleted, Simpson's space gets allocated, Simpson gets copied into it, and this pointer now points over there, and everybody's happy because Stu still has its pointer to valid memory. Alright. So we're going to have to make an assignment operator. We're also going to have to make a destructor. A destructor is the reverse of a constructor. It destroys an object. The destructor is necessary because when we're completely done with this code, and the stu object is no longer in need, we're no longer in need of it, we want to get rid of not only the stack space that stu uses, but we also want to get rid of all the heap space that stu uses. Particularly, we want to delete anything that was allocated off of the heap. And so the destructor is our catch-all place where we do that. We clean up everything once we're done with the object. And one more thing that we have to do. This is creating an empty student object and then assigning to it. There is another mechanism we could use whereby we initialize a brand new object based off of an existing object. The effect of this syntax is the same as this syntax, but it requires different implementations within the student class. Okay, this is an empty constructor or a default constructor that takes no parameters, and this one is the assignment operator. This is the copy constructor that takes a student object to copy to get the original. They both have the same issues, right? We want to make sure the assignment goes well. We don't copy pointers, we create new space and copy the data into the new space. Okay? So, copy constructor is another major issue for us. Okay, and that's where we're going to get today. assignment then is to take the last name, the first name, the email address, and make them dynamic memory. This style we're talking about over here. Social security number can still be statically sized. Why?
It's always doing the same size.
Okay, it's always the same. There's no need to mess with it, right? You still need your 10 accessor methods for your 5 data members. However, your accessor methods, your set methods for these 3 are going to have to change. Okay, we'll go through that. You're going to need a destructor, a copy constructor, and an assignment operator. Those things we're talking about over here. You're also going to have to do the output stream operator and 6 relational operators. We'll actually go through those examples on Wednesday. Using const correctly in all cases and make sure that you prove that it works. Okay, so let's remember last time we met we had this track object, this track type, to keep track of a track of music. We're going to modify it so that title, rather than being a fixed length, will be a dynamically sized array here.
So is that one already saved on the internet, and then you'll make a different one?
Yeah, that one's on there.
Is it?
Yeah.
Did it get uploaded?
Yeah.
Okay, good deal. So I'm going to keep this in the same folder so that you can compare them side by side. And let's call this one, I'm going to call it D track for dynamic memory track. Okay, so and rather than be creative, what? I'm just going to copy a little bit of code here. Okay, so D-track is the name of the constructor, right? Okay, so today we're just going to address dynamic memory issues that have to do with this. So this is starting off looking just like the other one. First issue, mtitle is not a statically sized array. Instead, it's a pointer to dynamic memory. And in addition to the constructor we have up there, we're going to have a copy constructor. A destructor. And an assignment operator. So from our class declaration, that's what it looks like. I wrote tilde student up here, right? So our constructor is always named after the class. The destructor is always named with a tilde in front of the class name. Destructor never takes parameters. You never call the destructor explicitly. It's always arranged for you. Either when a variable was declared on the stack and that stack scope goes away, the destructor is called automatically, or if you delete an object that was a class and has a destructor, then its destructor is called at the point you delete it, before its memory is actually freed up. Okay. Any questions in those 3 lines in particular?
Well, just the hyphen for D-track, that's...
It actually, my font isn't displaying very nicely on there. It's
that's
actually
a tilde?
the tilde.
Okay.
Okay, so we're generally okay. As your questions come up, please ask them. Okay, for the implementation file, I am going to start by just taking our original source code and replacing track with dtrack. And then we're going to fix it so that it works right. I'm additionally going to say we have 3 new methods, right? So those 3 new methods, I'm going to put their declarations in here. We'll fill in their details as we go. Okay, so here's our philosophy of dynamic memory. When we have a constructor, any constructor we have will make sure that a data member that's a pointer will be set up correctly. And by set up correctly, I mean one of 2 things. Points to something that was allocated off the heap using new, or we set it to the null pointer, which I will always write as 0. Put a slash that to indicate for sure it's a 0. So in a constructor, we'll always make sure that pointers start off in one of those 2 states. So this constructor here, we have mTitle, right? And so mTitle needs to either be set to the null pointer, that's option 2, right? Or it needs to be allocated from the heap. One of those 2. Now in this case, this constructor knows what the title is that's supposed to be copied there. It has data to copy in, right? And so because of that, we actually want to allocate memory. And so we want to go with option 1, not option 2. Is that okay? All right, how much memory? When I do new and I'm trying to allocate an array, I actually have to put some number in here. Usually it's in the form of a variable or an expression that's being calculated. But how many characters do I want to allocate?
Title in, amount, or size of title in.
Thank you. The length of title in, right? However many characters are in there, that's how many characters I want here. So I actually can get that using the string length function. And that's almost correct.
But that doesn't get the null character on the string.
That's right. String length doesn't count the null character, but we need space to store a null character. So we'll do a +1. Okay? So remember, string length is just counting the number of characters inside. Okay, I don't need that option. Now, since I have done that allocation, I should have enough room to go ahead and do the copy and copy data in, right? And I don't have to worry about my special case of capturing if they try to give me too much data. So it actually ends up looking a little bit simpler just because we're dealing with getting the right amount of space, so we don't have to have a special case anymore. Questions on that? Okay, I'm going to come back to these other pieces of code in a minute. Let's take the code we already have. Set length and get length don't have to change because there's no dynamic memory involved. Okay, get title returns the title, right? And so returning a pointer is the same as returning the name of an array, right? It gives us the pointer to the starting point of the array. So that doesn't have to change. Sets title does need to change. What's the process that set title needs to go through? if I have some object T here, which is one of my D tracks, and it has M title, which has a pointer over here to some data. That's the way it is right now when set title is called. We also have some stack memory, we call it title in. Which points to somewhere that has my new title stored in. In the end, when set title is done, if all goes well, this should be deleted. I should have a new array allocated with the new title copied to it, and mtitle should now hold that address instead. So that's the process we want to go through. Okay, so step number 1. Get rid of the old memory, right? Okay. This memory was allocated as an array of information, so it has to be deleted as an array of information. So I've got to put the brackets. The brackets are empty on the delete, which is nice. We don't have to remember exactly how big it was when we allocated it. Okay? That's step number 1. Step number 2?
Do new.
Okay. Get a new character array. How big does this new character array have to be?
The length of the title array.
Almost right.
+1.
Thank you. And what do I want to do with that new memory, or that new pointer that's given back? Need to make sure I save it off, right? So step 1 is we delete the old stuff. Step 2, we're now pointing to this new chunk of memory. Step 3. Copy the data in. Not too bad? So as long as we make sure we know what we're doing, we can methodically go through the steps, right? Okay, it's important that we delete before we allocate, because at this point we assign over the top of the old pointer, right? So we would be having some leaked memory, and even worse, if we deleted after we did the new, we'd be deleting the memory we just allocated, and then we'd be copying into it. So, gotta get the sequencing right, but other than that, it's pretty good. Okay, let me have you consider the 2 possible states that our pointer could have been in from a constructor. One is it points to new memory, and the other is it's a null pointer, it's a 0. So if it points to new memory, or memory off the heap, this is just perfect. But if it's a 0, this is actually going to cause our program to fail, most likely with some sort of memory access violation. Okay. On a Linux system, you'll get a segmentation fault. On the Windows machine, I think it says memory violation. The reason is you can't delete memory you didn't actually allocate. We didn't allocate the address 0. So we really should protect ourselves by making sure that there's something to delete before we call it delete. A little more complicated, but not too bad, right? So now we're handling the 2 possible cases. Either points to nothing, in which case we can skip the delete, or it points to something, in which case we need to delete. Okay? If everywhere in our code where we ever deal with this pointer, we always make this assumption, either there's something there and we deal with it, or there's nothing there and we deal with it, then we'll be able to handle this code very well. Make sure we always leave a function like setTitle with the same assumption. Either mtitle will be null or it will actually point to new data. And by the way, new will return null if there's an error, so it isn't unable to allocate data. So that's good. Okay, set title, get title, set length, and get length, all good. We can go back up to our other code up here. Let's first worry about the assignment operator. So on the assignment operator, we're receiving a dtrack object by reference. It's const to ensure that we don't make any changes. Let me just say that your intuition is that as a result of this statement executing, X will be changed, but Y will not be changed, right? You do have that assumption, right, that Y won't change? Okay. This const right here ensures us that we don't change Y. And if X and Y were track or dtrack objects, then Y is on the right-hand side of that assignment operator, right? That's why I call this RHS. That's a convention I use to keep myself straight. But RHS, short for right-hand side, it's the thing that we're copying from. Okay? We're sending it in by reference so that we actually are memory efficient and actually doesn't cause loops in what we're about to do. So we always want to pass it in by reference. But if we keep it constant, we make sure we don't make modifications in here. Otherwise, if it weren't constant, we can say RHS dot something and change part of Y, which would be unintuitive for everybody using your class, right? So we're going to try to follow convention here. Okay, so inside of here, we need to make sure that all of the data members get copied across. Well, M length is easy, right? Notice that since the assignment operator is a method of the dtrack class, it can directly access the private data even from the right-hand side because the right-hand side is a dtrack object. So we can just dot and access, we don't have to use the accessor method. Okay? Now, here's the tricky part. If I were just to do this, now we have a copy of the same pointer in two different objects, right? And that's the exact problem we were talking about, that we don't want to do this. So we have to handle this judiciously. We want to make sure that we actually copy the data appropriately, making sure that we free up memory if necessary. I mean, so if X already had some value here, so M title was pointing to some dynamic memory, and then later we reassigned it, we want to make sure we free the memory that was allocated here, right? So there's all the issues with M title, making sure that it's freed if necessary, and a correct amount of space is allocated, and then the data is copied, right? Same issues with set title, right? Wait a minute, it's exactly the same issues as set title. Why don't I just say this set title and pass in right-hand side's title? We already worried about all the issues down there, right? Does that make sense? Okay, so that's actually it. There's only the two data members. We've ensured that both data members get set up correctly. The only thing left is that when you return from an assignment operator, you always return star this. Remember, this is a pointer to the objects that's being modified. Star this is the object itself. And we're supposed to return a dtrack object by reference. The only purpose for that is it's possible to chain assignment operators in C and C++. So if you chain them, you want to be able to take Y's value, copy it to X, and then take the result of that and copy that to Q. And this returning the object that just got assigned to by reference allows us to keep the assignment going from right to left. You won't see me write a lot of code like that, particularly in a class like this, which is your first semester in C and C++, but you might see it in other code you see in the wild, so be aware. All right, but for now, if you just remember that we always do that, that's how we return from an assignment operator, you'll be fine. Okay, only 2 more issues to go. I'm going to skip the destructor and go up to the copy constructor. I love the copy constructor. We're trying to set up a brand new object, dtracked object, as a copy of an existing dtracked object. All right? SRC there, short for source. But this is if we're doing, just as a reminder, copying a track object U to initialize a track object T. That's the syntax that would spawn this. In that case, U would be passed in as SRC here. So this is so nice. That's almost the entire code for my copy constructor, if I already have my assignment operator working right. Assignment operator copies everything from this object into the current object, right? Doing whatever detail tracking is necessary for my class. And that uses set title and other things that are doing all those detail work. So this does all the copying. The only problem is here, remember set title assumes, so let's make sure we're following this. This calls the assignment operator, right? Assignment operator calls set title. Set title assumes that M title is either pointing to new memory or a 0. But this object we're working with from up here hasn't been initialized at all, so there's no guarantee that it's either one of those. So we just need to make sure that it's one of those cases. So as long as M title is initialized correctly, then the rest of this chain of code that gets called from here just happens for us, right? So we kind of built up from the bottom here to make sure that all the machinery is in place. Is that working? Okay, if that's working, let me show you the way I'd really do it. This syntax that you see here is specific to constructors only. And you can use this on data members of your class to give them initial values before the body of the constructor ever executes. So it's a shorthand for what you see right here, right? But it happens earlier. Is that okay to use on you?
Yeah.
If you don't like it, go back to the other one. They will both have the same result in the cases that we're dealing with. Okay, the only thing we have left to do then is our destructor. And in our destructor, we want to make sure that we have no dynamic memory left. We want to get rid of it all. So we want to delete this M title. Right? Okay, when we delete M title though, we always have to be careful. We might be in one of those 2 states, we don't know which. So, we first say if this M title, then we delete. Okay. Remember that 0 is interpreted as false, so the null pointer is really just a 0, so the null pointer is interpreted as false. So this code doesn't execute if M title doesn't point to anything. And then I'll just show you a little bit of paranoia that I have, that not necessarily everybody uses. But when I delete a pointer, I like to set it to the null pointer afterwards, the variable that's there, so I don't accidentally end up with a memory address. I somehow end up playing with it at another point in time. It's just my little paranoia thing. Okay. So the code that we have now is a dtracked object that is able to store arbitrarily sized titles and deals with them appropriately under all of these cases that we might want to use a student object. At this point, student object is no longer just, I'm sorry, the track object we're playing with is no longer fixed in its usability. It's a full class, it's a full object. It can do just about anything with it that we want to. So. If we write a test routine for it, copy one object. Let's see, 3 minutes is 180, so 78 seconds and we can then do things like VT. So we can print out T, U, and V, and we should get the same result from all of them, right? With all the copying, either the copy constructor or the assignment operators here, we never get to see the one hit by a wonder song. And then if we do something like, not that. Change the title on one of them. Let's change it on all of them here. Then we'll see that they don't affect each other. This is called other test. We will deal with those warnings at another date.
So
Yeah.
apparently you're not supposed to include a .cpp file.
That's correct.
Yeah, I didn't realize that. I was trying to get both the .h and the .cpp.
Oh.
Kept giving me errors and took a long time to figure out why. Why is that though, if you've got a short answer for it?
The TPP linked to the header, so we can include the header just contents as well.
Yeah.
Well, but I didn't have one of the, I mean,
So-
you know, at first I did have that, but after testing through it, I deleted the link to .h to .cpp and just tried linking it that way. But, you know, I did end up going back and
So
correctly, but
the design is that However many CPP files you have, each get compiled separately into object files. The object code down here has the actual machine code for only the functions that are defined in each of those. And then, through the link phase, you end up with the executable that combines all of those together. The header files that are included are so that A knows what functions are in B and C and vice versa. Okay, so that everybody knows what's in the others. If you start including the CPP files and then you compile all of them as well, if A included B.cpp, then A.O would include not only A's definitions but B's definitions, the actual code for it, as well as B would. So when you come to link, the linker will get upset because there are two different machine code definitions for a particular function, and now it doesn't know which one to use. The modularity that you get by separating out allows you to change code here without having to recompile these, and compile is historically a slow process.
I kept getting